One of the things I hope you learned tonight from the various talks, especially the ones from Thrust 2, project number 4, is that in order to have an organic electronic device, it has to be flexible. So nothing can just be straight on a hard backplane. This is actually going along with what Denise was saying. Everyone wants to have flexible displays, or at least it's this myth. And so this is actually a flexible display that came out by Sony at the end of last year. And so if you notice, this person is staring at this flexible display. It's somehow it's packaged, but it's also encased in this glass case. So if you look at this display right here, you'll see that again, it's in this glass case. Basically, it's one of those Embron glove boxes that they took the gloves off, so nitrogen's flowing through here to keep this thing alive. And we're flexing it for you. So you can actually see that it's flexible. Now, one of the things I did want to point out about this, and I'm using this as my motivation, is that if you notice it, that they're flexing it in a certain direction. And basically what they're doing is they're flexing this so that the display stays in compression. The other thing is that the contacts that are running to the display are sitting on the edges. And as I go through my talk today, one of the things you're going to find out is that with the contacts being on the edges, the stresses are the smallest. So one of the things that we really have to understand is in designing these, how do we design so that we spread the stresses such that these things will not fail? Okay, and so of course one of the things we do know is that we need to have encapsulation one day. Okay, so here's the overall story here is that we're looking for barrier layers that will actually protect the devices from oxygen and water vapor. Of course there are other degradation mechanisms that are basically factors that will cause the devices to degrade, but mainly we're looking at degradation of the contacts by exposure to water vapor and oxygen, as well as degradation of the active materials. So we want some sort of layer to go over the top of this such that we can prevent that those species from getting into the device. The other thing is that if we're going to talk about flexible, then we have to worry about any sort of mechanical damage that can happen to the device itself. So mechanical robustness of barrier layers, as well as adhesion and stress management across the devices. These are all part of the things that we have to worry about with encapsulation. So if you look at encapsulation overall, we have things like what the typical semiconductor industry will do. If we had our flat glass panel or some other panel, we can actually take some sort of a lid and seal it over the device and basically put a desiccant inside. And so the problem that we have here are basically the sealing materials. And so if we try to move to what we're showing you in the previous video, we're basically going to have something that is basically sealed around the device. Let's assume that this is our display material here. And so now we have to have very thin layers that prevent water vapor and oxygen, but that also can be flexed. And we also have these seals that we have to worry about. There are other techniques that you could do by vacuum depositing the encapsulation right over the top. But overall, we have to worry about the mechanical integrity and the transmission properties of these films. So basically, if you look at the food and pharmaceutical industries, they've basically dominated the barrier layer development for many years. But if we look at the requirements of what we have for OPVs as well as OLEDs, it sits down here in this area of, let's say, water vapor transmission rates, which I'll talk about, say typically less than 10 to the minus 4. If you talk to Konarka, that makes flexible solar cells, they're saying they only need something 10 to the minus 2, 10 to the minus 3. Not really sure how they're getting there, but most materials are, people are claiming they need something a little bit better than that for long lifetimes. And so we're going to talk a little bit about how do we get here from what the typical food and pharmaceutical industry is doing. Typically what's done is that you deposit let's say an inorganic film over the top of, say, your PET, PEN, whatever the plastic may be. The problem is that if you deposit these materials at very low temperatures, typically say 150 degrees C or less, then you end up with defects in these layers. And so these defects will allow the oxygen and water vapor to come through. So one of the things that we're trying to do in this project is look at ways that we can actually densify the films. And one of the techniques that people will do is also interrupt the growth of these defects by depositing multiple layers. So you deposit alternating materials, you prevent the defects from running from top to the bottom of the film, and that will allow you to produce better films. So part of the challenge here is to produce films with very few defects, and then also because of the cost issue, you need to be able to produce them very, very quickly and on a roll-to-roll basis. So here's my slide with key terminology. I mentioned water vapor transmission rate. It's basically the mass of water vapor which diffuses through a solid per unit area and per unit time, typically given in grams per meter square per day. The problem that you have with this is that water vapor transmission rate says nothing in here about the temperature at which I test or the relative humidity. So whenever someone gives you a water vapor transmission rate number, like I showed on the previous slide, you always have to ask them under what conditions did you test this? Because if you tested a different condition, you'll get a different result. So in order to compare apples to apples, you need that information. The permeability is more of a material parameter. Basically, you take your transmission rate, multiply by the film thickness, and divide by the pressure. And again, the permeability is at a given temperature, so that's the only part that you need to know here. The other thing is that people tend to get mixed up on, or maybe confuse a little bit, things like bend strength. We're starting to get into mechanics. So basically, this is the load at which a material undergoes nonlinear deformation, which we can call yielding, or it undergoes failure. So those are two different points. Another thing is that typically we call the strength of the material under a static deformation. One of the things that you'll find is that with brittle materials, there really isn't a true strength. It's basically distributed because of defects. So there again, you need additional parameters in order to really define what's the strength. There's fatigue strength. So if I have a material that fails at a given load, I can actually reduce the load so it doesn't fail under the initial application, but if I sit here and cycle it, eventually it may fail. And so typically we define the fatigue strength as usually the load at which the material does not fail after a given number of cycles. So we may pick the fact that we want to bend our flexible material 1 million cycles. So we'll find the load under which it doesn't fail at 1 million cycles. And the last thing is toughness. So toughness is basically the amount of energy that a material absorbs. So a lot of times people will say, I have a very tough material. If you have a tough material, it may not necessarily be very strong. So these are little things that come about when talking about the mechanics of what we want to see in our films. So overall, I want to have a material that it has high strength, and I may want to put a layer on top that's very tough. So if I have this material and I drop something on it, it's going to survive. Okay, so 2 minutes, all right. So I'll get through this quickly. So a couple of things that we're interested in is basically the principles of permeation. So basically, I can have a certain amount of water vapor that's sitting out here in the air. The amount of water vapor in the air may not necessarily be the amount that's in my film. So I have a certain amount that's actually absorbed, or a certain concentration that exists at the beginning, at this layer right here. And that's what gives me my concentration gradient in order for the flux to go through my film. I can actually go through differential equations and solve for the flux rate through my film. That's really not the important part that I want to show you here. The interesting thing is if I start stacking materials together, basically what I will have are materials that may actually absorb water, materials that are better at transport. So what I will have is that if I look at the mass of water vapor that goes through my film as a function of time, I have something that's nonlinear. So we call this the steady state regime. This is the transient regime. What does that do for my performance? What I will find is that under the transient regime, I have very small amounts of water vapor that actually go through. For a typical film that we've tested, this is about 1,300 hours. In the transient regime, the water vapor transmission rate is 8 times 10 to the minus 6. Under steady state, it jumps up 3 orders of magnitude. So that shows you that if I actually go and I run a test on my film only for a couple of days, I may actually get a false number of actually how this film is going to behave over a long period of time. So I really need to know both of these numbers, the transient rate as well as the steady state, and we're looking for ways to engineer in that transient rate so we can actually have better performance. All right, so moving on with the bending and flexure. So the flexural deformation puts one surface in tension, one in compression. So a lot of times you'll see, again, this is again from Sony, they're bending this thing in compression. Most brittle materials, they behave quite well in compression. So what happens if I take that display and bend it the other way? Those are kinds of things that we're actually studying in this project. The other thing is that I can play around with something called the neutral axis. This blue line right here shows me where I have basically zero strain, and I have to stop right there with the zero strain. So I will actually say, thank you very much for listening to me. Look at the pretty pictures. And the kinds of things that I'll just say the last thing, the kinds of things that we're trying to move forward with are understanding the mechanical behavior of the materials, testing things like the lifetime, trying to look at what are the mechanisms that relate to the barrier films and the performance of solar cells. These are some solar cells we have here. We've advanced some sealing technologies where we're looking at electrochromic materials, making those things flexible. These things have lasted for a few months now. And the overall impact is that we can finally take that Sony television out of the box. You can take it home, you can flex it, you can throw it against the wall. I don't know if you heard about in Atlanta, a guy just went into Walmart recently, and I think he took a baseball bat to about $20,000 worth of televisions. Well, he could hit that Sony television quite a few times, and that wouldn't do it. So I'd like to thank you for your attention, and have a good night tonight sleeping. Thank you.